Welcome everyone, and good morning, good afternoon, or good evening, whichever is appropriate to your location. My name is Brian Allen, and I am the Chief Metallurgist at DSI. Thank you for joining us for episode 18 in the Gleeble webinar series. We know how busy everyone is, so we appreciate your time and the time that you are able to devote to this webinar with us today. Today we have a very interesting presentation from Professor Joel Andersson. Professor Andersson is the head of the Division of Welding Technology at University West in Trollhättan, Sweden. The division comprises about 40 researchers, including senior researchers, PhD students, and engineers, and focuses on metallurgy, modeling of process physics, and process development and control. Professor Andersson focuses primarily on welding and weldability of high temperature materials, the precipitation hardening nickel and nickel iron-based superalloys. His talk today will present the University West Research Group and will discuss fabrication aspects regarding superalloys. Fabrication and welding of structural components for the hot section of aero-engines continues to be of high importance to the aircraft manufacturing industry. This webinar addresses weldability aspects and specifically hot cracking and strain age cracking phenomena that can occur during welding or subsequent heat treatment of precipitation hardening nickel and nickel iron-based superalloys. The influence of chemical composition in terms of hardening elements and impurities, the microstructure of the base material and the weld zone, together with the welding processes and corresponding parameters and heat input are discussed and related to the cracking susceptibility of different precipitation hardening nickel and nickel iron-based superalloys. As always, our goal will be to keep this webinar to 1 hour or less. If you have questions during the presentation, please submit them using the chat feature of the webinar. Our team will be available to answer some questions directly via the chat, and if time allows, we will have a question and answer session following the presentation with Professor Andersson. Video of this presentation will be available online soon, and certificates will be emailed to those of you who are listening to this live. You will be able to find a link to this video as well as videos of past webinars by going to our website, www.gleeble.com, clicking on the resources link, and then on the webinar button. There you can view past webinars and sign up for future webinars. Next week's webinar will feature Thomas Garson from Teknar presenting the science behind laser ultrasonic metallurgy and discussing the benefits of adding DSI's laser ultrasonic metallurgy or LUMET system to a new or existing Gleeble simulator. So without further ado, I would like to turn the presentation over to Professor Andersson so we can learn about the exciting work being done at University West. Professor Andersson, thank you for preparing this presentation. I will virtually hand the microphone over to you.
Thank you, Brian. Thank you for the comprehensive intro, and very glad to be invited to have this presentation for all of you. Hope you will enjoy it. And as Brian mentioned, I will talk and inform you about my university and a few things that we've been involved in from my group for the past years. Then I will also specifically talk about strain age cracking and one test that we worked on for the past 5 years. So I hope you will enjoy it. Basically, University West is the youngest university in Sweden. We started our activities in '89 as a request from local industries in the western part of Sweden, primarily former Volvo Aero Corporation and Saab Automobile, as well as a hydropower company called Vattenfall. They had a huge demand for engineers, so that's how everything started. So in '89 we started undergrad education, but officially University West was founded in 1990. So in '93 we had the rights to examine undergrad students, and in '94 we started the first research activities at University West. And at that time the research activities that we took on was related to thermal spray. So we have a very large and advanced facility with regard to thermal spray, and worked for many years, or since '94 then obviously, on the thermal barrier coatings, not at least together with Volvo Aero, but also together with the Siemens industrial gas turbines. And then in '99 we had the right to examine master students. So today we have about 3 different master programs tied to our production technology. So one of them is tied to robotic as well as automation, and the second one is on manufacturing engineering, and the third one that will start early next year is on additive manufacturing. In 2008, we inaugurated a large lab on production technology. So that's where we're located today. Been there for slightly more than 10 years now. And that's a lab that we named Production Technology Center, where we work closely together with the industry. So several industrial partners are located in the same building. That gives us a great opportunity to work together in developing various technologies. So the biggest partner or in industry located in the same building is the former Volvo Aero, nowadays GKN Aerospace. So we have many different projects together with them. And then in 2012, we had a right from the government to examine PhD students. But we have had PhD students long before that, but then I've been enrolled at older universities. So as I said, University of West founded in 1990. Our Vice Chancellor, Professor Martin Hellström, he started a couple of years back. We are roughly 700 employees and about 15,000 students, where about out of these 15,000 students, there are 5,000 full-time equivalents. And then the profile of the university is work integrated learning, which is something we try to implement in everything we do. And it's very much on how to couple theory and hands-on experience. So as one example, for instance, we have a fair amount of co-op education where the students spend a fair amount of time out in the industry. But with regard to research, we have a research environment called Production Technology West. And what you see here on this picture is the entrance of our lab, the Production Technology Center. So this research environment, PTW, comprise 3 different research groups or divisions. We have the division of welding technology, which I'm head of. As Brian said, we have about 40 people, and it's by far the largest research group on welding in Sweden. So as the name indicates, we do research as well as education on welding, but also on additive manufacturing. But then in terms of our responsibilities, basically welding-based additive manufacturing technologies. So then second group on additive and subtractive manufacturing methods has the responsibility of powder bed fusion, as well as thermal spray and machining and non-destructive testing. The third one is on production systems, where we do a lot of research and education on robotics as well as automation. So it's a quite unique research environment. We are close to 100 people. And as I indicated on the previous slide, we do dedicated research to many different disciplines like welding, thermal spray, machining, NDT, and robotics. And this is something we have seen to be very successful and come handy when we went into the area of additive manufacturing, because as you're probably well aware, additive manufacturing is quite of a multidisciplinary research area, which requires many different knowledge areas to come together to be successful in solving problems at stake. So what you see on the picture to the right is one of our laser welding cells, where we do laser metal deposition or direct energy deposition using wire with feedstock. So that's an area where we worked for more than 10 years. So the AM processes at University of West is basically what you see here. We do a fair amount of laser metal deposition using wire as feedstock, but we also do it with the powder as feedstock, the blown powder process, and together with others, we have a fair amount of projects also on powder bed fusion based on the laser source. And then we have an in-house system on electron beam, powder bed fusion, an A2X machine from Arcam, and we do also wire arc additive manufacturing, not at least together with the ESUB in Gothenburg. So within our research environment, as I highlighted, we do welding-based AM as well as powder bed fusion. And the welding-based AM is primarily direct energy deposition using either wire or powder. And we also do wire arc additive manufacturing. And then what we also do is a fair amount of testing to gain more fundamental understanding to what's going on during this type of processing. That's not only tied to the welding-based additive manufacturing, but also to the powder bed fusion processes. So with regard to the blown powder process, we have one key-ready system from Trump, as well as one system that we put together on our own based on gantry systems. So at the moment, we have 2 PhD students working on the blown powder process, whereas a separate welding cell based on the direct energy deposition using wire as feedstock is a process which we started to work on in 2006 roughly. And at that time we started to work on developing deposition, this specific deposition technology on titanium, and that was together with the former Volvo Aero, nowadays GKN Aerospace. So GKN Aerospace actually developed the technology till the point that they have the technology ready, and it's been out flying for several years now. So that has been very successful. The wire arc additive manufacturing is a process that we've been working on for several years as well. We work closely with ESAB as well as BAE Systems in Sweden. But as I highlighted just a couple of slides ago, we do a fair amount of testing, and not at least weldability type of testing. So I believe you had a talk by Professor John Lippold in the Gleeble webinar series, and I'm sure he went through this, but we acquired a new Gleeble 3800D systems, I think it was in 2016, and we have had several PhD students dedicated to this system. So I will touch base on that later in this talk here today, but primarily with regard to strain-age cracking. Then another thing that is very close to my heart is restraint weldability testing. So restraint weldability testing is more or less solely dedicated to hot cracking. That is cracking mechanisms that could occur during welding. So we are one of the few labs in the world who can do this type of restraint testing coupled to laser welding. So we do both laser assisted restraint testing as well as arc assisted restraint testing, and have several PhD students working on this. For powder bed fusion, as I said before, we do both laser as well as electron beam powder bed fusion. And at the moment we have 2 students working on the laser-based powder bed fusion, and about 4 students working on the electron beam process. So the laser base is in collaboration with others, not at least RISE, which is a research institute in Gothenburg, whereas we have an in-house system, an A2X machine on the Arcam, from Arcam. So for the powder bed fusion and the laser based, what we do there is primarily to work basically on both processes. We work on the nickel-based precipitation hardening superalloys. So for the laser-based system, right now we have some work on the 247 LC alloy, which is a very high precipitation hardened superalloy. For the Arcam machine, we do a lot of work on alloy 718, the workhorse within the aerospace engine materials. So are there any interest in additive manufacturing? I guess the obvious answer is yes. And if we check the number of publications versus years, we can see that there has been a tremendous boost in the amount of publications for additive manufacturing, exponential growth. So it seems like a lot of people are working on AM. And then another question is, where does most of the AM and specifically the powder bed fusion research take place? We look at the different countries where we can see publications coming from. We can see that most of the publications and research seems to be carried out within the G8 countries, with a couple of exceptions of China and India. But then you might be aware of the fact that a big and promising market for, not at least for powder bed fusion, is aerospace. But then when you look at powder bed fusion as coupled to superalloys and compare that to the overall amount of publication within powder bed fusion, the amount of publications connected to superalloys is significantly less compared to what's going on overall. But nevertheless, it seems at least to be a dramatic increase also in powder bed fusion connected to superalloys, as also seen for the publications or the research carried out for all other materials. And if one consider or go back historically to look at high quality production of wrought superalloys, which basically requires for critical components, let's say rotating turbine discs, etc., we always require triple melt sequences regarding the primary manufacturing sequence, like vacuum induction melting and electroslag remelting and vacuum arc remelting. These type of processes and production are also normally associated with the G8 countries. So this is actually true also for powder bed fusion connected to superalloys, but here with the exception of China and Sweden. And an interesting thing that I would like to inform you or tell you about is the history of powder bed fusion here at University West. Roughly 3 years ago, we decided to go all in, so to say, on research regarding powder bed fusion of the workhorse material 718. And we've been very successful in bringing in funding to start up our research on powder bed fusion. So what you see here is a fair amount of projects. It's not all the projects that we have in our portfolio, but it's most of the projects that we have internally at University West. And what you see here is not only connected to powder bed fusion, but also to metal deposition or direct energy deposition, wire arc additive manufacturing. So you see some numbers here in terms of funding, and if you divide by 10, you get it in a rough estimate of euros or US dollars. So what is interesting is that we started about roughly 3 years ago, and when I checked the amount of publications within the area of powder bed fusion as connected to alloy 718, we can actually see that the research group that we have here at University West was the group that published most within this area. So here you see, instead of University West, you see the Swedish name Högskolan Väst. So this is something that at least it tells us that the effort we made paid off. So what are the drivers then for additive manufacturing? Well, when considering aero-engine or aerospace, light and strong materials required for a successful flight. And there was one guy who he figured this out many years ago, and he designed this machine. That maybe you know who it is. It was Leonardo da Vinci. So he realized that, okay, in order to be able to bring something up in the air, we need light and strong materials. And the Wright brothers, they actually realized this as well. But the Wright brothers were very lucky. In fact, extremely lucky, because the engine block that they made for their engine was made out of aluminium. It was a cast engine block, and They were lucky because the material hardened by coincidence. So that probably made it, was one reason for the successful flight. So light and strong materials are very important for aerospace. And that a driver to that is to make things hotter and better. So if we consider superalloys, and specifically the precipitation hardening nickel-based superalloys, one driver or ambition is to use materials that can sustain a higher service temperature compared to, let's say, the standard workhorse 718. So one way to accomplish that is to add more aluminium and titanium to the chemical stew. So aluminium and titanium, they push up the amount of hardening phases, or hardening phase, specifically the gamma prime strengthening phase. The problem is that if you push the gamma prime content up the roof, you get a very bad processability, or a very high risk of cracking, not at least drainage cracking. So it's always a balance in terms of service performance and processability when you develop a new alloy. But here, additive manufacturing, and especially the powder-bed fusion processes, seem to provide a route to explore these more crack-prone alloys that has been impossible to weld by normal welding processes in the past. So I guess one reason for this is the more confined melt pool that you have during the powder bed processes, and also the ability to actually tailor or adjust the melt sequence during processing, which is not as easy for conventional welding processes. So the diagram you see here is a diagram that is heavily used to describe the materials or superalloys inherent resistance to weld cracking, and it should specifically be used for strainage cracking, but many times it's mistakenly used also for hot cracking. That's a big mistake. So the importance of welding and also additive manufacturing then. Well, one of the major drivers for welding is what you see here, that is fabrication of aero-engine components, and not at least the structural components that you can find in all our commercial jet engines, as well as the military ones. But here you see the GKN Aerospace engine specialization. So you have some highlighted parts on the schematic commercial jet engine on the top right. And on the very rear end of the aero engine, we have a turbine exhaust casing. So in the picture, you can see one of these turbine exhaust casings, and this tech or turbine exhaust casing is a part of the Yandex engine, which is one of the largest commercial jet engines in the world, and placed on the wings for the 787 Dreamliner, for instance. And this type of structural component it's a load-bearing component, so it has to sustain a very high amount of load. Meanwhile, it also suffers from a fairly high temperature. But there is a lot of weld to perform this type of to build this type of component. So roughly about 60 meters of weld is required to actually build this type of component. And what GKN do is that they have developed a fabrication concept to produce these components. That is why it requires a lot of welding. So by traditional means, this type of component has been cast as a single piece castings. But by fabricating instead of casting this component, one can actually tailor the component in a more efficient way. So what they can do or accomplish is that they can reduce the weight significantly on these components, and they do that by combining different types of material forms, like combining sheet and forged as well as cast parts. and they join them together by welding. But it also offers the opportunity to add different materials, so one can use more sophisticated materials where you have more stringent requirements and less expensive superalloys where you don't have as high demands. So this is extremely important to increase the efficiency of the new jet engines. And here additive manufacturing is another tool in the toolbox as compared to wrought materials or forged or cast materials. So AM provides an additional ability to even further tailor this type of component. But then another concern concept plays, and that is every material forms like forgings or castings, for instance, have its inherent history and susceptibility to cracking, for instance. And AM is also a new type of material forms. So if we consider the size of the chambers, production chamber for powder bed fusion, we can realize that the chambers are quite small, and we need to actually utilize welding to produce these larger components. So welding of AM produced parts is extremely important, and that's an area which has not been really fully explored. So we just recently had I had a student who graduated during the springtime, Tahira Rasa. She's now continued to work as a lecturer here at University West. She looked into restraint and as well as Gleeble testing of AM produced powder bed fusion produced alloy 718. And we could see, for instance, that it's very important that you connect the way you build the part, which will affect the grain morphology and the grain orientation of the AM part, that you think of the build direction as well and connect that to the weld preparation later, because the grain orientation and the grain size significantly affect the weldability of the material. That brings me to weldability, and I'm sure that other speakers have touched on this before. Basically, weldability can be a bit arbitrary, as you have to be careful when you use it, so you define what you mean by it. But basically, I think this, I stole this from the American Welding Society. So basically, they refer to 3 different categories. The first one is metallurgical capacity, basically how easy or hard it is to weld something without forming any deleterious constituents. The second one deals with mechanical soundness, which refers to how easy or hard it is to join or weld something without forming any discontinuities or pores or shrinkage, slags or cracks. And then the last one refers to serviceability, that is how the weld will perform during service. So from our research perspective, most of the research projects that we have refers to weldability and specifically to cracking susceptibility. So when you deal with the cracking susceptibility and the superalloys, it's primarily hot cracking, which could be at stake during welding associated with the liquid phase, as well as strain edge cracking that are at stake. So strain edge cracking is also at high temperature, but it's at the not necessarily involved in the liquid phase. Cold cracking could be a concern, but it's not a big issue with the superalloys. So here today I will show more towards strain edge cracking. So basically, strain edge cracking is something which is highly connected to the precipitation of hardening phases in the precipitation hardening nickel-based superalloys. And one could say that the standard grade alloy 718 was developed in the past because the industry suffered severely from strain edge cracking in Waspaloy and other alloys, and demanded a new alloy which had less propensity towards strain edge cracking. So alloy 718 is more or less immune to strainage cracking, but that is because it's primarily strengthened by gamma double prime and not gamma prime. So gamma prime is a precipitation hardening phase that precipitates very fast in the material, whereas gamma double prime takes much longer time in comparison. So as I said, alloy 718 is primarily gamma double prime hardening alloy, whereas Waspaloy and Haynes 282, for instance, are gamma prime hardening alloys. And one of the problems is then that when you do post-weld heat treatment, you enter the precipitation nose of the gamma prime hardening alloys. So basically, as you weld something, you get contraction in the fusion zone, and this contraction in turn produce stresses and strains in the heat affected zone. And during the post-weld heat treatment, you get hardening, and as a consequence of this, you might get cracking. And this type of cracking usually takes place intergranularly. So there are various influencing factors regarding strainage cracking, and as I said, it's primarily something for the precipitation hardening alloys, but specifically for the gamma prime hardening alloys. So aluminium and titanium are the two key elements regarding the gamma prime phase formation. So the more you have of aluminium and titanium, the more gamma prime you have, and the higher the risk of strainage cracking. Then carbon content has also been shown to have a high importance. Carbon is a carbide former, of course, and the carbide formation at the grain boundaries can sometimes prevent grain boundary sliding, which can be beneficial towards strainage cracking, as well as for ductility dip cracking. Then there are other minor elements like sulfur, boron, phosphor, which also have some effect. In terms of microstructure, grain size is the same as for hot cracking. Smaller grain size is usually beneficial because you increase the grain boundary area, and which put less demand on each grain boundary. Homogeneity, for instance, castings are usually more susceptible compared to wrought materials. Welding process, the more heat input, the more weld restraint you have, the worse it gets in general. And then when it comes to investigation of strainage cracking mechanisms, there are various routes to go. To make it fairly simple, one way or one group belong to the so-called representative type of tests, whereas the other one belong to simulative type of testing. So recent PhD student of mine, Fabian Hanning, he worked on this for 5 years, and he graduated during spring, and is now working as a postdoc in my research group. And what we did there was to do extensive amount of representative type of testing. Representative type of testing is usually something which is easily done, but the problem is usually that it's hard to get fundamental insight to what's going on, or how to explain the actual cracking mechanism. So then the simulative type of test comes more handy, and is a way to actually provide more insight to the fundamental root cause of the actual mechanism. So there are different ways to assess strainage cracking also with the simulative type of tests, and a lot of tests has been developed using the Gleeble system. And I think the most successful test has used the Gleeble system, but there have also been tests developed with the simple tensile test machine and halogen furnaces, etc. The constant load rupture test is one test which has been used to predict strainage cracking, which is assumed to measure the time to failure. What we have seen in the literature, though, is that it does not predict very well. And then we have the stress relaxation test, which are intended to give more insight to the ongoing mechanisms. But the problem with this is that it's quite hard provide material rankings with this type of methods. They are quite tricky to perform. And then we have stress to fracture tests, but these tests do not really indicate any resistance towards strainage cracking. You might have material being providing high stress during fracture, but it doesn't say anything about the susceptibility towards strainage cracking in general. And my favorite are the tests referring to measuring of ductility. These type of tests can be used to rank materials, and there are different methods. So the ductility type of test is what my former student Fabian Hanning went into. So quite some years back, I saw a test. I think it was Metzler at Haynes International who developed it, and he did really nice work where he ranked different superalloys. And basically, what he did was to simulate a post-weld heat treatment cycle. And what you do is that you have a slow heating up to a certain test temperature or soak temperature, and then you slowly pull the sample to fracture, and then you measure the reduction in area and plot that versus the test temperature. What I added to Metzler's test was a heat affected zone thermal cycle, because I thought of the importance of actually lightweight the grain boundaries in the heat affected zone before you do the actual post-weld heat treatment. So this is something which gave us a tool to make very good rankings of various alloys as well as heat treatments. But to be honest, it does not really provide very good understanding for the root cause to strainage cracking. So benefits were, for instance, it was very easy to use this type of test, and the relative performance in between the different materials and rankings were good. But as I said, no insight to the actual mechanism, like the influence of precipitates, as well as the count for heating rates and exposure times becomes a bit tricky. So Fabian Hanning, he developed a new test where we decided to, I have a video here that I will show you. And basically, we have the sample, and instead of a slow heating rate, we heat up in a very fast manner, and then after a certain exposure time or dwell time, we pull past the fracture. So by doing this, we could vary the not only the exposure time, but also the dwell time or the test time, and to systematically investigate what happens as we change test temperature as well as exposure time to get more insight to what's going on in the material. So here are some of the results that we did on Haynes 282, which is a reasonably newly developed superalloy. So to the left-hand side, you can see the reduction in area versus test temperature with varying exposure time. So we can see by increasing the exposure time, ductility drops. And the ductility drop is most significant for temperature 850 and 900 degrees C. And we can also couple that to the strength of the material, in this case, hardness. We see increase in hardness by increasing exposure time at these different temperatures. So ductility decrease as a function of exposure time, and that correlates to the onset of the gamma prime precipitation. So we couple this type of testing with the sophisticated characterization using transmission electron microscope as well as scanning electron microscope. And we did it not only for 282, but also for Weldability and some other materials, and it's all published in different journals. So to summarize, I could say that fabrication of aero-engine and specifically hot structural components is very complex. AM can be seen as an enabler, but it also adds complexity. there is a lot of different thermal profiles that can be complex and create a lot of different phase reactions during processing. And most of the research on powder bed fusion is carried out in the G8 countries, with few exceptions: China, India, as well as Sweden. Jumping from AM to strain edge cracking, what we can see or conclude from our research as well as from the literature is basically weld restraint and precipitation induced stresses have a significant impact on strain edge cracking, as well as then on the ability to relax residual stresses. The kinetics of the hardening phases is influenced by the chemical composition, as well as the dislocation density, which in turn affect susceptibility towards cracking. And fine grain size is very important. Finer grain size, beneficial. We saw this very clearly in the research we did. And that in general true also for hot cracking. But then, just to round off this Gleeble talk, is there any future for Gleeble? I hope that you don't lose your breath now, Brian, but it seems quite promising. When we look at the amount of publications for Gleeble, we can see that it's increased quite dramatically for the past years. And I just searched for Gleeble. You see that we reached almost 500 publications a few years back. If we combine Gleeble and the welding, we can divide the Gleeble publications by 10, and then we get roughly 50 publications annually for the last year. We look at the amount of publications for the different countries. You can see that China is the country producing most of the publications by far. If we combine Gleeble with welding, we can see that the US gained some publication on China, but China is by far the biggest country. We look at the different research groups. You can see that there are mainly Chinese groups on the top when it comes to Gleeble publications. But when we combine Gleeble and welding to the publications, we can see that the University of Manitoba is on top there. Happy to see that, because I'm also a young professor at University of Manitoba. But then we have other universities as well coming shortly behind. Looking at the different authors, I believe most of the authors on the Gleeble publications are from Chinese affiliations, but for Gleeble and welding, they are a little bit more spread on the globe. So it seems like Gleeble has a great future. I think that's a nice way to end this talk. Thank you very much.
Okay, thank you very much, Professor Andersson, for that wonderful presentation and some very interesting statistics on the Gleeble use that, of course, us at DSI are very interested in and try to keep up with and follow ourselves. So again, thank you very much. We do have a few minutes for some questions. So if you have a few minutes, Professor Andersson, I'd like to present some of the questions that our viewers have submitted into the chat site here. So. One of the questions we have is, are there any guidelines for SAC testing for the solid solution strengthened alloy, superalloys like alloy 617? So it's a bit of an open-ended question, but maybe you could comment on that.
I'm not sure, to be honest. So I can't really answer that. Not to my knowledge. I'm not aware of any standardized tests.
Okay, very good. Is there any effect of impact loading type of application or other environmental conditions other than temperature on SAC?
It depends what you mean by impact loading. You mean when you use the Gleeble?
The question is is what I read. I'm not sure that I can elaborate on it, but maybe the asker can.
But I mean, for instance, if you do, when you do the loading in Gleeble, let's say the first test we worked on and the one that I believe Metzler developed was based on a fairly, we exposed the sample to a slow strain rate. So that will for sure affect the ranking and the outcome from the test, because as you induce dislocation and increase the dislocation density, you will increase the kinetics of the precipitation of the gamma prime phase. So that has an influence. But I'm not sure that that is what the question was referring to, but that's how I judge.
Okay, very good. Maybe a kind of a related question is there an influence of the strain rate on the results of SAC?
Yes, that is basically what I said. So
Yes.
strain rate has an importance, definitely.
Okay, what is your idea about solid state welding of AM superalloys?
I never dare to go into it. It's quite demanding. One of our senior professor, Johnny Adjoni, he's going wild on friction stir welding in our group. So I wouldn't be surprised if he's trying to move into that area, but I haven't dared so far.
Okay, very good. For SAC testing, is there an applied stress prior to the heat treatment to account for residual stress simulation and stress relaxation during heating, or do you just pull to failure after aging at temperature?
What we did was just to pull to failure after heat treatment. We did not have any pre-stress.
Okay, just kind of my own personal thought. Would you expect there to be any kind of a effect of a pre-stress, say a residual stress existing in component?
Yeah, I mean, the more pre-stress you have, the worse it gets, in my opinion. So that's one reason why residual stresses has an impact on strain edge cracking. But if I'm right, what we did was to have it in. We tried to have it in zero. I don't know what you call it, you Gleeble guys. I said it, but zero force control. So we try to keep the load as small as possible, and when we reach the specific temperature, we pull to fracture. That is, if I recall correct. Fabian might be mad at me now if I say wrong. But,
Okay, very good. How can we differentiate between DDC and SAC?
Well, DDC is not really associated with precipitation hardening phases. It's more related to carbide precipitation. And strain edge cracking is primarily associated with strengthening phases like gamma prime. And one thing with the gamma prime phase is that I think one of the concern why there is a problem with the gamma prime hardening alloys and not with the gamma double prime is that the gamma prime phase has a smaller lattice structure compared to the austenitic phase. So that means that when you have precipitation of the gamma prime phase, the phase precipitates homogeneously inside the grains, and the smaller lattice distance of the gamma prime phase induce a negative lattice mismatch, which in turn induce tensile strains on the grain boundaries. So that's kind of the fundamental explanation of why we suffer from strain edge cracking. So it's the negative lattice mismatch that is the reason for strain edge cracking.
Okay, very good. Has your group been involved in any development of new nickel-based superalloys?
We have been involved in some of it, but I cannot talk about it.
Okay, so that's proprietary information right now.
Yeah.
Okay. So there is a question, is there any scope for other researchers to do any collaborative manufacturing, additive manufacturing research work with PTW or University West?
Can you repeat that question?
Yeah, we have a question about whether there are any opportunities for collaborative additive manufacturing research work with your group.
Absolutely. Just contact me.
Okay,
we are always open for collaboration.
Okay, and your email address is, I believe, showing up on the screen right now. So
yeah.
So
and I can also stress, take a look at the YouTube link that you see there. Then you can see a glance of our production technology center. But we collaborate with a lot of other universities around the world. So happy to extend that, definitely. And not only universities, also industries, of course.
Yes, of course. Okay, thank you very much. One more question: how to get fine grain? How can you get a fine grain zone at the cracking region? I guess that is asking how to try to minimize the grain size in that region.
Yeah, you try to develop fine grain structure to prevent cracks, not just to have the fine grain size surrounding the cracks, but there are different routes to make that. I have another PhD student working on the ARCAM system, for instance, and there we fine tune certain parameters like the line offset, etc., to create or develop more of a equiaxed structure compared to these columnar grains that you usually see. So there are different ways to tailor the microstructure. Then, of course, heat input is one obvious challenge. The more heat input, usually the larger grain size you get.
Okay, maybe one final question. We had a question of what was the device that was clamped to the specimen between the jaw grips in the Gleeble test that you showed? I don't remember that photo, so I'm not sure I can answer that question.
Let's see.
I don't.
Device, you mean this? It's just a holder for the quenching system.
Okay, yes, yeah, so that is our standard gas quench head nozzle. So just to try to answer the questioner's question, it's not really clamped to the system, it's actually behind it, and it's the gas quench nozzle that could be used to cool the sample, but I don't believe you did a quench in this work, but so.
No, we used air cooling.
Okay, well, very good. Well, we want to be respectful of everyone's time, and we're approaching the 1 hour mark now. So we want to thank everyone again for your participation in this webinar, and remind you again that we'll have another webinar next week covering the laser ultrasonic metallurgy system, or the LUMET system, that is available for Gleeble simulators, and we hope everyone can come and learn about that system as well. If you have any more questions for Dr. Andersson, or if you would like to connect with him directly, please feel free to reach out to DSI, and we can share that contact information. And actually, that contact information is on the screen right now. So I believe he's indicated that it would be okay to contact him directly. If you have any technical questions about the operation of your Gleeble, please contact our service team. As we mention every week, we have a new service portal that includes a very useful knowledge base and a very convenient service ticketing system. So current Gleeble customers can create an account for that service ticketing system by clicking on the resources link in the top navigation bar at www.gleeble.com, and then click on the customer support portal. If you have any questions about how a Gleeble can support your work or your research, please email our team, and we will be happy to connect you with an application expert and work with you to find the correct solution to your research needs. Thank you everyone for joining us. Please stay safe and please stay healthy. Thank you.